Okay, let's go ahead and look at a piecewise function. Now for a piecewise function, usually the function looks different over different parts of the domain. So for this piecewise function, I'm going to define it as f of x equals x plus 1, but only for values of x that are greater than 1. And I'm going to let this equal 1 over x, but only for values of x that are greater than or equal to 1. Whoops, I got to make a change here. This greater than right here should actually be a less than. I would not have a function unless this was defined as a less than. So clearly something's going on with this graph. It looks like it could be going on at 1, x equal 1, so let's go ahead and have a look at this graph. The first part of this is easy to graph because it's just a nice little line. This is the graph of x plus 1, which has a y-intercept of 1 and a slope of 1. So here's my y-intercept of 1 and a slope of 1. Now if I go ahead and plug 0 in, 0 plus 1 is 1, I get 1 back out. If I plug a 1 in, and you might say, well, wait a minute, you can't plug a 1 in because this is only defined for greater than 1. But I'm going to go ahead and plug a 1 in and then remember that it's actually undefined at that point and put in a hollow point. So if I plug a 1 in for this function, 1 plus 1 is 2, I will have a hollow point there. And that gives me my idea of my slope. And there's the graph of x plus 1. Now I can't graph it further up here because it's not part of the domain. The domain is x less than 1. Now for 1 over x, let's have a look. Let's go ahead and plug in a 1 to 1 over x. If I plug in a 1 for 1 over x, I end up with a 1 back out. If I plug in a 2, I end up with a 1/2. And this is what my graph will end up looking like. It will approach, as x approaches infinity, the graph will approach 0, get closer and closer to the y-axis. So again, clearly we have a little bit of an issue here at 1. What's going on at 1? So I want to determine if I have continuity at x equal 1. So do I have point continuity at x equal 1? Now remember, there's 3 criteria. The first criteria is the limit as x approaches, in this case 1, of my function must exist. So I'm going to write out the criteria and then try and determine whether I meet that criteria or not. Okay, so limit as x approaches 1 from the left, limit as x approaches 1 from the right. And that should look more like a plus sign. Okay, let's go ahead and approach from the right. As we approach 1 from the right, my x value, x is approaching 1 from the right, my y value is approaching 1 as well. And in fact, it actually equals 1 from the right. Now from the left, as I get x equal closer and closer to 1, my y value is getting closer and closer to 2, but notice that I never actually equal 2. These are not equal, therefore the limit as x approaches 1 of f of x does not exist. And I'm done. I don't need to really check anything else because as soon as I fail to meet one of those criteria, I'm done. So therefore I have a discontinuity at x equal 1. And in fact, it's a jump discontinuity. Now, what about continuity at 3? Yeah, that looks pretty reasonable, and I can go through and check that process. What about continuity at 0? Yep, looks reasonable. I can check that process. Now my next question is this graph, f of x, right continuous or left continuous? And from observation, we can see that I do have a defined point here at 1, 1. So I know it can't be left continuous because I'm undefined here, but I am right continuous because the limit from the right is equal to the functional value. So I do have right continuity. And the reason I have right continuity is the limit as x approaches 1, not c, that's the general definition, x approaches from the right of f of x is equal to 1, and f of 1 equals 1. So this is my first criteria, this is my second criteria, and my third criteria says the limiting value is equal to the functional value. Therefore, I have right continuity, because again, I'm only checking the limit from one particular side. Okay, now we can look at the last type of discontinuity called an infinite discontinuity. So there's three types of discontinuities. Oops, continuity. There's a removable, a jump, and an infinite discontinuity that we're going to be looking at. So we get an infinite discontinuity if one or both of the one-sided limits is infinite. And we've actually come across quite a few graphs that have that idea of infinity involved. Let's go ahead and look at f of x equals 1 over x squared. Here's the graph of f of x equals 1 over x squared. If we were interested in this as a limit as x approaches 0, we can see that they would agree at infinity. The limit from the right is infinity, the limit from the left is infinity, therefore their overall limit is equal to infinity. Therefore the limit does not exist, because an infinite limit is not a limit at all. So this is an example of an infinite discontinuity at 0. I could also have a trig function. Let's go ahead and look at the trig function. F of x is equal to the tangent of x. You should be able to graph the tangent of x pretty easily. Remember, the tangent function is equal to sine over cosine. So wherever cosine is 0 is where I'll have a problem, because we don't want that denominator undefined. So cosine is 0 at pi over 2 and at negative pi over 2. And the tangent of 0 is 0, and it's an increasing function. So here is one period of your tangent graph. Guess I didn't quite need all of this over here. So there's one period of the tangent graph. Well, let's go ahead and try and determine the limit as x approaches pi over 2 from the right of tangent of x. And actually, the rest of the graph over here would look as such. Okay, and it would come up over here as well with another asymptotic line. So as we can see, as we approach pi over 2 from the right, this is going toward negative infinity. As we approach pi over 2 from the left, put in tangent of x here, we can see that we get this positive infinity. Now the limit from the right does not equal the limit from the left, therefore the overall limit will not exist. These are not equal. Therefore the limit as x approaches pi over 2 of tangent of x does not exist. So therefore I have a discontinuity at x equal pi over 2. And that was pretty obvious because I have a vertical asymptote there. So that seemed like a really reasonable thing to come to a conclusion on. Now we also have some other theorems on continuity that your book gives you. Theorem 1, you can read through it's pretty self-explanatory. And also with Theorem 3, they're talking about when you can expect particular functions to have continuity. Now in your homework on this section, you have some pretty complicated graphs, and I would encourage you to use Maple to look at those graphs to determine continuity, but also apply these laws to determine continuity as well. So again, Maple is really good for graphing, and it gives you a good idea whether a particular function is continuous or has continuity at a particular point. Maple's not so good, because remember, with Maple they don't show hollow points, and a lot of times with their asymptotic lines they connect their asymptotic lines, so you do have to have some knowledge about those particular graphs before you plot them. Piecewise functions in Maple are pretty easy to work with. If you need some help in Maple with piecewise function, I would encourage you to type in a help command like piecewise function or define domain, because you have to restrict the domain for a piecewise function. Let's go ahead and look at one last example. For this example, we're going to be looking at another piecewise function, except this piecewise function is not totally defined yet. I have this unknown value of c, and the goal here is to find the value of c that makes the function continuous. So in this particular case, we're going to force continuity. The easiest thing to do to start is to look at a little bit of a graph. Both of these are lines, so they're easy to plot, and I can see right off the bat that something's going on at 3. X equals 3 seems to be important. So those are some points that we'll definitely want to focus in on a little bit. It looks like our scale is going to have to be not just 1 unit up on the vertical axis. If I plug 3 into 2x plus 9, I get 15 back. So let's go ahead and plug in the 0.3, and we'll say that we get the 0.15 back. So if we scale this, let's go 5, 10, 15. Okay. Now also for 2x plus 9, I have a y-intercept of 9. So this gives me an idea of what my graph looks like. Now remember, the domain for 2x plus 9 was just x less than or equal to 3, so I'm only choosing values less than or equal to 3 in the x direction. So that's why I only have the left-hand part of this graph here. Now, negative 4x plus c. Negative 4x plus c, I do not know the y-intercept, but I do know the slope is negative 4, and I know it's only defined in this direction. Now, what's going to be true is if I want to force continuity, that if I plug a 3 in, I have to get a point that is going to be covered right here at 15. If I had plugged a 3 in and had, let's say, a hollow point down here, I'd have a jump discontinuity. So I want this hollow point, if I plug 3 in, to go right on top of this filled point, so I'll have continuity. So in order to have continuity, at x equal 3, what must be true is that negative 4x plus c has to equal 15. Okay, so solving through, I get c. Actually, let's back up here. We have to plug in 3 because they gave us this value of 3, and then we can solve. So I have negative 4 times 3 plus c equals 15. Negative 12 plus c equals 15. And then, of course, adding across to both sides, I get c equals 27. Therefore, this second function has to be negative 4x plus 27. So if c is 27, I'll have continuity here. So if I graph negative 4x plus c, my slope would be negative here, something like this. Now this part is not defined, but we can see if we were to extend it, I would have a y-intercept clear up here, and 27 does seem to be a pretty reasonable value. But that's the value of c that forces this to be continuous. Piecewise functions are going to be very, very important. Being able to talk about left and right continuity will be important as well. I would definitely be able to graph a piecewise function by hand. For the piecewise functions, we're going to be looking at basic functions like polynomial expressions, 1 over x, trig functions, sine, cosine, tangent, 1 over x squared, just some real basic functions like that in the piecewise functions, maybe some absolute values as well. But definitely be able to work a lot of the piecewise function type problems by hand, because those piecewise functions are where we have the problems with discontinuities. Thank you.